Hello students, today I am going to discuss Poynting Theorem. So this theorem is proposed by John Henry Poynting in 1884. What this theorem tells us that what will be the power flow? What will be the power flow from time varying E and B fields, that is electric and magnetic fields? What will be the power flow? So this theorem is valid for say, for any arbitrary time varying fields. Will be deriving this some equations, some vector we will be deriving. Okay, so we will be getting a vector from this theorem, and this will give the power flow. Okay, so let us consider that EM wave is propagating through a conductive medium to a conductor, and what can happen is if there is charge particle within the conductor, then what will happen? The energy of that EM wave will decrease. That means it will lose some energy, right? Because EM wave will definitely interact with charge particles. So we are in a festive mood now. So we have Durga Puja. So if you have gone for pandal hopping and it is lot of crowd, then what will happen? You will feel uneasy, and you will feel the hindrance in movement. So you will be hindered, right? Because there is a lot of crowd around you. So what will happen after say 2 or 3 pandal hopping? What will happen? Oh, I can't walk anymore. I lose my energy, so I need something. That means you are losing the energy due to the environment or the environment through which we are passing, or the medium through which is passing. Similarly for the EM wave also, the energy of the EM wave will decrease if it is propagating through a conductive medium. Okay. Later we will see how much it will be attenuated or how much will the EM wave be attenuated. So we will see that later. So in this context, I can give an example. Say all of you heard about microwave. So in microwave, what happens is that EM waves basically interact with the food particles, and on the food particles we have the heat generated, and that is why the temperature rises. Then we get the the food is getting warmer or hotter. Okay, so you're getting say good food, hot food. Okay, so this can be a practical example you can relate. And as you know, we are discussing EM theory or EM wave subject. So what we need to rely on say Maxwell's 4 equations. So you can see the 4 mantras. Okay. So here we need to choose two Maxwell's equation. One is for the curl of E, one is for the curl of H. Okay. So you know these 2 equations. You are familiar with this. I have already discussed in the class. And remember one thing: this H and E, they are basically the field intensity. They will represent the field intensity. E is for electric field intensity, H is for magnetic field intensity. And your B and D, they are nothing but the flux density. One is electric, one is magnetic. Okay, so this you know. And J is of course the current density. Okay. So with the help of these 2 equations, we will be deriving the Poynting theorem, and we will be getting ultimately a Poynting vector. That will ultimately give us a knowledge on how the power flows, or what amount of power flows, say through a surface or something. Okay. So to derive that, the starting point can be that from the vector identity we are choosing this. Say we have chosen this vector identity. That is the divergence of 2 vectors, curl of 2 vectors is basically this much. That is, here I have chosen A and C as arbitrary vectors. You can see this can be any vector. Okay, so here I have chosen A and C. So divergence of curl of A and C is basically, or you can say divergence of cross product of A and C is basically the dot product of C and curl of A, and it should be subtracted with the dot product of A and curl of C. This is, you know this. You can refer any 11, 12 physics books, you will get this. Okay. So this is for any two arbitrary vectors. So we are discussing about EM waves. So what we have electric field, magnetic field associated with it. So you can replace these two vectors by electric field and magnetic field. So let us say we write A as E and C as H. Okay, then you get this equation. Okay. Now, if you carefully see this, here we have a curl of E, here we have a curl of H, and from Maxwell equation, you know what is this curl of E. Curl of E will be minus mu del H del T. Remember this del, sometimes they will call del, sometimes a curly D. It is basically representing the partial derivative. Okay, and this one, curl of H, is basically your J plus permittivity of the medium through which it is propagating, and we have the del E del T, or curly D E basically. So I will say del. So del T, del E del T. Okay, this is from Maxwell's equation. Okay. So I can rewrite this equation like this. Say we'll be getting the divergence of cross product of these two fields E and H. It will be basically H dot product with minus mu del H del T minus E J plus permittivity, and you have del E del T. Okay. Don't forget to keep the vectors notation. So vectors like it should give. Okay. Had this epsilon is the permittivity and mu E is basically permeability. Okay. So this is what we have got. Remember one thing, what we have done here is basically, say if I go to the previous page, so you know that B equal to mu H and D equal to permittivity to electric field intensity. This you know. And what we are considering here, that this mu and epsilon is basically constant. Okay, so it is not changing. Okay, and another thing we are considering, that the medium is isotropic. So our medium is isotropic. That means, what is the meaning of isotropic? Isotropic means your electric parameters will be independent of the direction. So electric properties of the medium are independent of the direction. Okay, so electric properties means your flux density, electric field intensity, that is. So isotropic medium. Okay, so that means we have D and E. That means D and E both will be in the same direction we are considering. So two things we are considering. One is the medium should be isotropic. That means your D and E are in the same direction, and your permeability and permittivity, they are constant. Okay, and they are basically scalar quantities. Okay, and this J, you know what is this J? J is basically, you can say, from Ohm's law, microscopic form of Ohm's law, that is J equal to sigma E. Okay, this is microscopic form of Ohm's law, where sigma is the conductivity. This is the conductivity, and J is the current density, E is the electric field intensity. This you know. Okay. Now what we have is, just remember this equation. I mean, just focus on this equation. And now we'll be doing some adjustments to replace some of the terms in that equation. Okay, so what we have, say del t of any two vectors, say A and C. I am considering any arbitrary vectors. Okay, any arbitrary vectors. If I consider the dot product of these two vectors, and if I take the del t of that dot product of two vectors, what we have? We have A dot product with del C del t plus C dot product with del A del t. Okay, so these are the two. This is the, you can say this is also a type of vector identity. This you can calculate. Okay, now suppose we have same vectors. Say same vectors. Suppose same vectors. Same vectors means, so I want to say that A equal to C basically. So for same vectors, what will have, this equation will become, say del t A dot A. There should be a vector notation here, and it should be equal to, A dot del A del t plus A dot del A del t. I have replaced C by A only. Okay, I have replaced the C with A. This is what we have. Okay, so basically these two terms are same. So if these two terms are same, what we have? We have 2A del t dot product. Okay, so this we can have. Okay, so this we can write. From here, what you can write is A dot del A del t. It is half of del t A dot A. This we can write easily. Okay, that means I have taken these two on the left hand side. Simply I have done that. Okay, now this A dot A, how can I write? I can write at half del t, and it is mod A square. Okay, mod A square, because you know A dot B, say any two vector, the dot product will be mod A mod B cos theta. This you know, since here we have A dot A, that means we have mod A again, and cos theta. Theta means the two vectors are same, that means theta will be 0 degree. That means what we have? Mod A squared. Okay, so this is what we have written here. Okay, this is what we have written. So what we have this term is basically nothing but this term. Now see this one and this one. Can you find any similarity? See this term. See this one and this one. There should be a dot product here. So you will see the similarity that we can replace that equation. I am considering that permeability and permittivity be constant, so you can take it outside. So what you can write? We can rewrite this equation with the help of this part. So this one you can say this part is total part is just an simply adjustments you have done to replace these two terms on the right hand side of this equation, this main equation, say equation number 1. So these are the extra adjustments what you need to do to simply replace these two terms. These two terms will be replaced, this one and this one. Okay. So let us see what we have. Ultimately, if I use this terms, then what we'll have, if I use that relation what we have derived, we'll be having this divergence of E cross H will be equal to minus mu by 2 del T mod H square minus permittivity by 2 del E square del T, and we have a sigma eta, sigma E square. This, remember, we will be having say Je, and J is nothing but J equal to sigma. Okay, so if you see this, we have a J here, right? So we have a J. We have a J here. This J we replaced by sigma. Okay, this we have replaced. This is what we have done. Okay, and we have taken the mu and the permittivity outside, and simply we will be getting this equation. You can check. So this is the equation what we are presently standing. This is the equation. Okay. This equation what you have derived is basically for a point on the space. That means this is a point relation, and this relation should be valid at every point in the space at every instant of time. That means at every instant of time, at every point in the space, this relation should be valid. That means what we have written. Okay. Now suppose we are considered a volume, and if we integrate over that volume, then what will happen? Simply by integrating over a volume, what will be the thing? So integrating over a volume, say V, divergence of E cross H, this will be equal to, need to get the dV also. This is basically del V, and this total thing dV. Okay, so this much will be copied here. Okay. Now this is a volume integral. I told you. Remember, we are integrating over a volume. What we have derived, this is for a point, and if you want for the whole volume, simply need to integrate over that volume. That means you need to calculate the volume integral. Now what we can do from here is by divergence theorem. You know that divergence theorem. By divergence theorem, I can change this volume integral to surface integral. So I can write this as, say, surface integral surface S enclosed by the volume V. This will be E cross H, just E cross H, say dA, or say ds. Okay, that's for the, say, let us write ds, and this is of course will be a vector. Okay, so this is the left hand side we have written like this, but simply applying divergence theorem. You know the divergence theorem, right? That means surface integral, it will relate surface integral and volume integral. Okay, and we are keeping the right hand side of the equation as it is. Simply we are not doing anything, simply we are keeping it as it is. Okay. Now what you can do here, let me write this. Right hand side I am not, left hand side I am not writing, I am writing the right hand side now. Okay, so what we have, minus, it should be the volume integral, it should be mu by 2 del t h dv minus volume integral of permittivity by 2 del mod e square by del t dv minus again the volume integral sigma mod e square dv. This I have written from this equation. Okay, and integrating over the volume. Okay, separately I have written. This is one term, this is one term, this is another term. Okay, now if I take this del t outside of the integrals, all del t, if I write outside of the integrals, I can do that because my volume, the volume which I have considered is constant over time. So if it is constant over time, that means I can take the del t outside of the integral. Okay, then what we have, we can write the equation like this. So we have left hand side, we will be keeping it as it is. In some book they will say dA, they will write. Okay, no need to worry about that. We are considering a small area, say dA, small area dA. Here I am writing ds. Okay, so what we have, we can write this minus del t. So I am taking the del t outside of the integral and we are integrating over the volume, and we have mu by 2 h square mod h square dv plus volume integral v permittivity by 2 mod e square dv. This much what we have, minus the j term, that means that sigma e along with the e, sigma e square d. This is what we have, this is e. Okay, so this is ultimately what we have. This is the left hand side and this is the right hand side. This is what we have. Now we will see what these terms will represent. Okay, so we will see that what these terms will represent. Okay, so first of all, the term, will start with the term this one, what this total term is representing. Okay, remember this part, this one is basically represent the the magnetic energy stored in the volume V. This is the magnetic energy stored in the volume V. Magnetic energy. Okay, and we are taking the del t and with the integration, so it will be the rate of change of magnetic energy, right? Rate of change of magnetic energy. Similarly, this one this term is simply the electric energy stored in the volume V. Okay, and since we have a del t outside, so what we have, it is the time rate of change of your electric energy. Time rate of change of electric energy. Okay, over the volume V. And we have a negative sign here. We have a negative sign here. That means that energy, the time rate of change of this energy, these two energies, one is magnetic energy and the electric energy, they are decreasing. Okay, so they are decreasing. So ultimately, this term, you can write it, is giving the rate of decrease of total energy. Total energy stored in the volume V. Rate of decrease of total energy stored in the volume V. Now, rate of energy means nothing but power. So basically this is decrease of or decrease in power in the volume V. Okay. So this is what we have. In some reference you will see they will write this as this part only as mu h, sorry, UH, and this one as UE. This representing the energy per unit volume. Nothing but energy per unit volume. Why per unit volume? See, we have a volume multiplied here. So if you want the energy, so this term should be energy per unit volume, and this one is the magnetic energy per unit volume. This UE is basically the electric energy per unit volume, or you can simply keep it as it is. No need to write UH and UE. I'm just saying, if you follow any other reference, you will see UH and UE. So don't get upset or what is going on, what this term is. So it is nothing but that energy part, energy per unit volume. Okay, so what you have understood right now, that this term, the first term of the right hand side of the equation, is telling us that decrease in power in the volume V. Okay, so I hope it is clear. This is for first term in RHS. First term, considering I have considered this as a whole. Okay, this is the first term. First term. Okay. So this is one thing. Second, we need to discuss the second term of the right hand side equation. What is that? Again negative. We are having this sigma E square dV. This is basically the ohmic power loss in the volume V. That is, it is representing the EM energy converted to heat per unit time. It is the amount of electromagnetic energy converted to heat per unit time. So this is nothing but your ohmic power loss. Okay. This is ohmic power loss, and it is representing that your EM energy converted to heat per unit time. Okay. So I will explain this more. This one, this term sigma E square dV. So you can see this should be some, say, energy per unit volume. This term should be energy per unit volume, because here you have a volume multiplied. This should be energy per unit volume. Okay, so we will see, or you can say this is energy spent per unit time in volume V. Okay, this total term is the energy spent per the EM per unit time in volume V. This is the term. Okay, so we will see what is this sigma E squared term doing, what it is representing. So let us see. So we know the Lorentz force. Lorentz force, I hope you know. So if an EM wave finds a charged particle in its way, it will apply a force on that particle, right? So if an EM wave finds a charged particle, any charged particle, in its way, what will happen? It will apply a force on that particle, and since EM wave we have electric fields and magnetic fields associated with it, so what you can have, the force should be that force should be, say, the Lorentz force. QE, this is the electric force and the velocity into the magnetic field. So this is the Lorentz force. Okay, so this is Lorentz force. This you know. This is due to the electric field, the force due to electric field. This part along with the Q, it is the force due to the magnetic field. So this is the force acting on the charged particle. Okay, and we know that power. What is power? Power is nothing but your energy per time. Okay, so you can say the work done. W is the work done. So work done per time, per unit time, it is nothing but the power, and W, this is work done, I can write it as force into displacement. So let us say force into displacement, I can replace this W by force into displacement, say dx. Okay, so this can be the same. W is the work done, and you know work done. What is the formula for work done? Force and displacement. Okay, now see this dx dt, this term, this is distance by time. I mean, I am not talking about the change. Okay, so just I am giving you the what can be the unit or what can be the term. Just I am giving the idea what can be the term. Note, we are writing dx dt, that means we need to take the change in distance and change in time. But simply I am telling this distance by time, this will represent the velocity. Okay, so what we have? Simply what you can write is force into force velocity. You can say dot product. This is the dot product, so this should be dot product. Okay, so this you can say. Okay, so now this force we can write, this force we can replace by the Lorentz force. So QE plus QVB, this should be dot product with the velocity. Okay, so this we can write. Okay, so what I am doing from here, basically I am trying to show you what is this sigma e square, what we have derived, what is that term representing. So this is what I am trying to give you the idea. So we form the Lorentz force. Lorentz force, you know the force due to electric field and magnetic field, that is given by that equation, and then you have the power. What is the form of power? The change in energy by unit time, energy per unit time, energy the the work done. So work done, you can write it as dot product with force and displacement. From there you have seen that your power should be force into velocity. I mean the dot product of force and velocity. Okay, and this is what we have done. Now see, this is for one charge particle, that is the force acting on one particle per unit volume. Now if we have say n particles, say n particles, n say number of particles per unit volume, if I consider this, what we have? Simply this power will be nqe dot velocity. So what I have done, simply multiplied this equation by n, and remember this term, or no need to, I'm not talking about any, you need to remember this term will be basically, this dot product will be 0. I hope you have understood why this is 0, because see, say two vectors A cross B, dot product with A, this has to be 0. Why? Because we know that the cross product of any two vectors should be perpendicular to A and B. That means the cross product of any two vectors should be perpendicular to both individual vectors, and means your A cross B, this vector, A cross B, it is perpendicular to A as well as perpendicular to B. Okay. Now if you take the, say this is a vector, this is a vector, and they are making 90-degree angle. So what will happen? So dot product, you know, it should be, say the angle will be 90-degree. So we have dot product, in dot product we have cos 90-degree. So cos 90-degree is basically 0. From that you will see that you will get the 0. Okay. So if you write this in terms of magnitude and angle, you will see that angle made by these two vectors is 90-degree. From here you will be getting 0. Okay, so this term will be basically 0. That is why I have written only this much. Okay, and of course q is constant, so I have taken the q outside, and in these are constants. Okay, so what this term is basically giving us now, since we have added an n here and we are taking n as per unit volume, so this power will be now power, not just power, it will be power per unit volume. This term. So power per unit volume will be NQEV. This is what we have got. Okay. Now NQE, you know, this NQE, this is nothing but your G. Right? Sorry, not NQV, NQV basically. So we can write NQV dot E. Just simply these two vectors I have interchanged due to the, I can do that commutative property. Okay, so NQV is basically your J, okay, the current density, and J dot E, this term is basically your power per unit volume, J dot E. Okay, so what we have seen that power per unit volume is basically your, again I am writing once again just to make it clear, NQV into E, this is what we have, and this NQV is nothing but J dot E, and you know J is basically sigma E. So from that what we can do is sigma E dot E we can write, and this we can write as sigma E mod E squared. How we can write this? We have already explained that two dot product of any two vectors will depend on just the magnitude. Okay, so this is the term. So what you have seen is basically, I want to focus on this sigma E squared. This term is nothing but power per unit. Okay, so this the last two pages what I have derived. This is not required for examination purpose, but I have given just an idea that what this term is signifying. This term is signifying. So this is giving us the power per unit, this much. And when this power per unit volume is multiplied by volume, we will be getting the power, and we are integrating, so the total power, and there is a negative sign. That is, again it is representing some decreasing power per unit volume. Or that is, you can say the energy per unit time is getting decreased. Power is energy per unit time. So you can write it in the form of power or energy. If you write in energy, then you should write energy per unit time. Okay. So this is the thing. This sigma E squared. Sigma E squared. This is basically the loss. Okay. Power lost per unit volume. So you can write it. This is power lost per unit volume. We have the negative sign there. Okay. So that is why we say that energy spent by EMA per unit time in volume V, or the power lost in volume V. So power lost per unit volume. Per unit. Okay. So this is the significance of the second term. So second term is representing the power loss from the, this is the power loss, the ohmic power loss. So this gives the ohmic power loss because we have conductivity here. Okay. So this is, I told you, ohmic power loss. Remember, this is not the ohmic power loss. This is power loss per unit volume. So you need to multiply. That means I am talking about this term, the second term. That is this term. This term is only the power loss per unit volume, or the power per unit volume multiplied by the volume, and you have a negative sign. This actually gives the ohmic power loss. Okay, so this is the ohmic power loss. Okay, so this is the significance of the second term of the right hand side of the equation. So this A and B, what we have discussed, one is giving the rate of decrease of total energy stored in the volume V, that means the decreasing power in the volume V. This is also saying the ohmic power loss. So total, you can say the power loss from the volume, that is the right hand side is giving, that means A plus B, these two terms are giving us the power loss from the volume. Power loss from the volume. Both are giving the total power loss from the volume. Okay, so on the A is giving the rate of decrease of total energy stored in the volume B, or decreasing power in the volume B, and it should be, say, added up with the ohmic power loss. Okay, so this is the significance of these two terms. I am only talking about the right hand side of the equation. I will be coming to the left hand side in just say in just 1 or 2 minutes. Okay, so this right hand side part is giving the power loss from the volume, and since there will be no other loss in that medium, okay, there will be no losses in the medium apart from these two, so there will be no other loss. Okay, because we have seen mathematically that we have only two terms. So this is just giving the total power loss from the volume. There will be no other losses. So what can happen is that we need to maintain the conservation of energy. So if we want to maintain the law of conservation of energy, so this power loss should be equal to the power leaving from the volume V. So this power loss, that means the power loss should be, why this power is getting lost? Because the power is leaving from the volume. That is why it is decreasing. Okay, so in order to maintain the law of conservation of energy, this power loss should be due to energy leaving the volume. So that means, simply, if I say in a simple word, that the left hand side of the equation, that means I am talking about this one. This left hand side of the equation should represent the power coming out of the volume. So net outward power coming out from the volume. Okay. And so basically the net outward flow of the power should be equal to the rate of decreasing power. That is what is this total equation signifying. Okay. So net outward flow of power, or net outward power, say W, capital W, this should be your left hand side of the equation. Surface integral of E cross H ds. Note ds should be a vector. Okay. So this is basically your net outward flow of power. The total term is representing. But you can see from this equation that this term is basically nothing but power density on the surface of the volume. That means if I consider a surface, consider a volume, on the surface what is the power density this E cross H term is representing. Why? Why? See, this is nothing but a surface integral, right? This is a surface integral. That means this term has to be power density because it should be multiplied by this area. So this should be power per area. This term should be E cross H should be power per area. Then only if it is multiplied with area, then it will give the power only. So because this is a power, I told you this is the power, and since it is a surface integral, it is the outward flow of power from the surface. Yes. Okay. So this has to be this E cross H. This has to be the power density. Okay. That is why I have written power density on the surface. Okay. So seeing what is there after the term, that is what is the ds, we can easily see that this is nothing but a power density. So E cross H is just giving a power density or power flow per unit area. So you can say power flow per unit area. This is what I am trying to say. This term is nothing but your E cross H. This is what we have. That means this term is giving the power flow per unit area. And when you take the surface integral with this, we will get the total power flow. This you have understood because we have already discussed surface integral, line integral, volume integral. I have given the total concept, what is the surface integral and what should be the concepts behind it. So E cross H is giving the power flow per unit area. This E cross H, this is nothing but your Poynting vector, and it is represented in some book you will see say P, or in some book say S, like that. Of course it will be a vector sign which should be. So some books you will see P, some books you will see S. So this S is basically your Poynting vector and nothing but E cross H. So if you take the cross product of two E and H, it will signify that, it can signify that it is the power flow per unit area. Why say there is a possibility that this term is giving, it will give the power. In most of the cases it will give the power, that is the power density, power flow per unit area, except some other cases where this is not giving the power, because it can happen that even though at some point this P or E cross H exists, even though at some point on the surface P exists, P means the E cross H, there is no net outward flow of the power from that area. There is no net outward flow. This can be the scenario. At any point it is finite, but when I am talking about the whole, that is when I am talking about the net power flow from the area, that can be zero. Okay, so it is, you can say that this information, this E cross H, this can give the information about power. Not always it can give. It can give. Okay, so not always it can give, but for our discussion we can say that it will give the power flow per unit area. It will give the information of the power. Okay, I will give the again example where this Poynting vector, I mean E cross H, failed to give the information of the power. I will make a scenario on that. But before that, so this is the Poynting vector what we are going to know. And this surface integral, this left hand side, that is the surface integral, this surface integral of E cross H over a closed surface is equal to the total power leaving the closed surface. That means the total power what is leaving from the surface, total power what is flowing out of the surface is nothing but the surface integral. This is basically your Poynting theorem. So what I have written here is basically Poynting theorem. So outer flow from the surface should be equal to the surface integral of cross product with E and H, cross of E and H. Okay. And remember one thing, this Poynting theorem is valid for only a closed surface. Because every time, see, if I am giving this sign, the circle sign, to represent that we are dealing with the closed surface. That is, it is not a point relationship. It is not a point relationship. So there are certain cases, there are certain classical cases you can say where it contradicts the use of point relationship of the point vector. Okay. That means what I am trying to say that maybe, as I told you, that maybe at some point on the surface this P exists, but there is no net outward flow of power. Okay. There may be a scenario. I am giving an example, but this concludes the idea about Poynting vector. So remember, it will be valid for, for time varying fields. Okay, because E and H we are considering as time varying fields. This you need to consider. Okay, so be careful while applying Poynting theorem. You should the field should be time varying in nature. Okay, so this is what I want to say. And as I told you that P can exist, but P means the Poynting vector, or you can say S. The S can exist at a point on the surface, but there is no net outer flow. I am giving an example on that. So what we have seen that your Poynting vector is given by E cross H. This is what we have seen. And this is valid for closed surface. This is not a point relationship. Not necessarily it is a point relationship. That means at every point on the closed surface, this use of this E cross H is basically arbitrary. Okay, so there are certain classical cases which contradict the use of this point relationship for the Poynting vector. Point relationship means this is the relation what I have written is valid for a point. Okay. So in some cases it may be contradicted. Okay. So I am giving an example of the case. Here we have drawn a magnet, and let us see we put a charge here, positive charge here, and say at the point, says we are considering a point P, say here, and we have the south pole and north pole like this. So basically the charge is on the north pole, and if I see at the point P, this is the direction for say H, and this will be the direction for E. That means the E should be along the line joining the charge and the point. This is the charge, this is the point. If I draw a line, the electric field should be along that line only. Okay, so this is the direction of E, and H is tangential to these lines of force. Now you will see that this S, say S means the Poynting vector at the point P, it is given by E cross H. Fine. Now the question is whether it is finite or zero. So if you see the picture, this E and H, not parallel to each other. If it is not parallel to each other, that means SP will be finite. That means SP will be non-zero. Why? See, if we have two vectors, say A cross B, like this, okay, it will be 0 when these two are parallel to each other. So you know that A cross B, you can write it as mod A mod B sine theta. And if theta is 0, that means they are parallel to each other. When the two vectors are parallel to each other, their angle is 0. Then only this cross product can be 0. Okay. So for this case, we have E and H, and we are saying they are not parallel to each other. If you see this E and H, they are not parallel to each other. So SP will exist, and SP, the direction of SP will be outward from the plane of the paper. Outward from the plane of the paper. Because you know that S should be perpendicular to E and H. Because for the cross product will be always, the direction of the cross product will be always perpendicular to the direction of the individual vectors. That means if I say A and B, here we have the E and H. That means the direction of this pointing vector should be perpendicular to both E and H. Okay, that is, for this case it will be outward from the plane of the paper. So if there is SP, that means if it is finite, pointing vector, that means it is signifying that some power is coming out of the plane of the paper at the point P. Some power is coming out from that point. But that is not the case, right? Because we know for this case there will be no sustained power flow. So this is contradictory. That means SP is signifying that there will be a power flow, but in reality there is no power flow. That means even the SP is finite, there is no net outward flow. Okay. So if I consider another point symmetrical to this P, say P dash, here we have the electric field direction, say like this, and H will be like this. Since the P and P dash, they are symmetrical to each other, that means the magnitude, say SP dash, the magnitude of SP and SP dash will be same, but the direction, their direction is opposite. Because for the point P dash, if you see that SP dash, the direction will be, the direction of the pointing vector will be inward to the plane of the paper. So that means for P it is outward, for P dash it is inward. I am talking about the direction of SP. Okay, so they are opposite in nature. That means opposite in direction. The direction is opposite. So ultimately the sum, the net, will be 0. Magnitude same, but the direction is different. That means the net sum will be 0. Okay. So this can be so at this situation, what we are seeing, that if we calculate the pointing vector at any point, we are getting a finite value, even though there is no net outward flow of power. But this type of pathological cases, except for this some pathological cases like this, pointing vector can give, or you can use the pointing vector to find the power density at a point in the space. So this pointing vector can give the power density at a point in space most of the time, but not necessarily every time it will give the information of the power or the correct information of the power. See, in this case, even though the power is 0, the net outward flow power is 0, the pointing vector is giving a finite value. This should not be the case. Okay, that means there should be parity between the outward flow and this pointing vector. But for this case it fails. But these situations are very rare. For our course, for what we study, most of the practical cases, you can use this pointing vector to find the power density at a point in in the space. That means you can use it as use this relation in point form. Okay, so generally we use this as a point relationship, although it is not strictly a point relationship. Not strictly a point relationship, but we can use it because this type of situations what I've just discussed just now is basically not too often face. In practical applications or in practical in for practical cases, you will see you can use the Poynting vector, no problem. You can use the Poynting vector as a to get the estimate of the power density. You can use it at some point in the space. That means if you want the power density at a point, you can use the relationship. That is what I am trying to say. But it is not every time it will give this correct result. There may be some exceptional cases like this. Okay, but you can use it for the practical purpose. Okay, so this is all about the Poynting vector and Poynting theorem. You need to study this Poynting vector and the total whole equation what we have derived in the say the last in this page. Sorry, not in this page. This one, the top one, the green one. The green equation you should remember, and you should understand each and every term. And remember this power flow, that means the direction of this S what we are discussing, that is the direction of S, that is the Poynting vector. Sometimes they will say S, sometimes they will say P, something like this you will see, right? The direction will be always in the direction of propagation of the wave. Remember this. S will be along the direction of propagation of the wave. See, EM wave is a transverse in nature, and E and H, they are perpendicular to each other, and E and H individually they are perpendicular to the direction of propagation of the wave. Since E and H are perpendicular to the direction of the propagation of wave, then you see the Poynting vector is also perpendicular to E and H. We have seen that, and because it is an E cross H, we are taking the cross product, so S has to be perpendicular to E and H, and then obviously S will be in the direction. So S, the direction of S will be in the direction of propagation of the EM wave. This is very important. Okay, so I hope you have understood the thing. We will, if I miss anything, remember this is this theorem you can apply for a closed surface and for time varying fields. Okay, so if I miss any point, I will discuss that. I will cover that when we will solve some problems, some numerical problems on this. I will cover that. Okay, so stay safe and stay healthy.